All right, so we are doing the second part of our two-part synthesis today. We are doing an, okay, so this is two-part synthesis, week 2, all right, intro, okay. We are doing an elimination reaction, which in some respects is, you could almost think of sort of the opposite as an addition reaction. Okay, so rather than reacting an alkene and adding atoms to each carbon of the former alkene, we're sort of doing the opposite work. Taking away atoms from two adjacent carbons, okay, and creating a double bond. So on one of the carbons, you need a leaving group. Okay. Oh, what am I talking about? We've already talked about eliminations extensively in here, right? You guys did eliminations. You did an E1 elimination, right? Right? Sure. just not. You don't even have to need it. Just not. Remember we did with the cyclohexanol. Yeah. We made a good leaving group. We made a carbocation, adjacent carbons. We took a proton, stuff like that. But that was an E1 elimination. We call it an E1 elimination because in the critical step, there's only one component, the starting alcohol in that particular reaction. The starting material that has the leaving group. That's the only species that's doing anything in the critical step, otherwise known as the rate determining step, so that's E1. In an E2 reaction, there are two critical things in the critical step, because it's a one-step reaction, actually, for the most part. There's a base, so the base and the leaving group do their things in the same step. All right? Now, one thing about an E2 elimination is it wants to go through something called periplanar geometry. Okay? So it wants to be in the same, the leaving group and the proton want to be in the same plane. Okay? You know that we're talking about tetrahedral geometries on all these adjacent carbons and stuff. So they could be any which direction. Okay? The proton that's going to get taken off and the leaving group that's going to go need to be in the same plane. Okay, not at crazy angles. Right? And they need to be 180 degrees from each other. So it's actually anti-periplanar geometry. So proton, leaving group, like this, in the same plane. Not like that, that's no good. Okay, in the same plane. All right. So we can depict that. So E2 favors anti-periplanar geometry. Okay. So this is probably not this is a way of drawing you probably haven't even seen yet. Organic chemists got all ways of drawing stuff. This is called a sawhorse projection. Okay. But I mean, there's nothing fancy about it. Just try in your mind's eye. So that's a tetrahedral center. I'm trying to depict the tetrahedral center. Those and those are sort of sticking out that way. And so this one and this one, they're in the same plane. So what an E2 elimination wants is it wants the leaving group in the same plane as the proton. Okay? And now the base comes along, these electrons slam down, and the leaving group leaves. Okay. Now, so why is that? Well, they want to be in the same plane because remember what they're doing. They are actually, those carbons are going to rehybridize to sp2, okay? And this particular orbital, okay, that's overlapping the proton's s orbital. So the orbital that this carbon is using is an sp3 orbital. It's going to rehybridize to a p orbital. So it's going to go from sp3, which looks kind of oblong-y, to a p. Not really a p, but and then it will, and this carbon's going to do the same thing, okay? And then they're going to overlap each other. Well, it turns out that if so let's okay, those are the two orbitals that are going to rehybridize to I only had half my coffee there. 2p orbitals, imagine. So these two guys are going to be sort of shifting up and rehybridizing and beginning their overlap. Okay? If you have sort of this big lobe sort of begin to overlap with that little lobe, you get, and then the same on the bottom, you start to get better overlap as they are shifting if they are pointed in the opposite direction. If they were pointed in the same direction, you don't get very good overlap on one side of that alkene early on. Okay? So as this is trying to form, you get better overlap, more equivalent overlap top and bottom of the alkene, for lack of a better way to say. And that brings down the energy of activation for doing this reaction. Okay? That's why they like. I mean, I think you can obviously see why they want to be in the same plane, because those guys got overlap. You know, if one was cockeyed like that, and one was like that, then no overlap. So it makes sense that they got to be in the same plane. But this hopefully gives you an idea of why they need to be anti to each other. Okay? All right. So let's look at we are actually doing, in order to do our reaction, we are doing 2 successive E2 eliminations in a row. Okay, so they also, the faculty support normally prints out my lecture notes, so I have no lecture notes, it's all up here. Goodness gracious. Alright, I'm going to convert that to one of those sawhorses. Makes life a little bit easier. Alright, so those guys are in the same plane. Bromine, H, bromine, okay? That's, if you just kind of rotated that guy a little bit, it should sort of line up in your mind's eye with that one. Yeah, bromine's sticking out at us. That bromine's sticking back. All right, so our leaving groups for this are going to be, we can pick either one because we're going to do both of them eventually, but let's make that the proton we're going to pull off, and that's going to be the leaving group. So we need to do some rotating here. All right. So let's rotate that front one. put the H down. Okay. If I put the H down, the bromine's going to go there, and the benzene ring's going to go there. I now will rotate that one up. Okay. That's going to stick that H there, and then that benzene ring there. Okay. Now, our today's base is potassium hydroxide.
Is potassium a counter ion?
One more time?
Is potassium like a counter ion?
Yes.
Okay.
Oh, sorry.
Sorry, yes.
This is actually my better side. That's cool. I don't have one. This is my better side. All right. Okay, so the entire very planar. Yay, E2's happy. Comes in, grabs his base. Those electrons slam down there. Okay, leave. Now, yeah, we talked about last week. We talked about cis and trans alkenes. We also talked about E and Z alkenes. Okay. Just looking at the orientation of this Sawhorse projection, when we get our product here with this new double bond, are the benzene rings going to be cis or trans to each other? You know, the lobes are going, those carbons are kind of flattening out. Cis or trans? Sorry. Cis. Yeah. Yeah, they're both. I mean, it's like sort of. All right, there's that benzene ring, and then that's the benzene ring. This is the bromine. They're just going to kind of flatten out, really. That's all they're going to do. And same with that back one. Yeah, just going to kind of or flatten up in a sense. Okay. All right, so. Right? Okay. Now, using the other type of classification, is that an E or a Z alkene? Are they estranged from each other? I give you guys these little nuggets of funniness, free of charge.
Sorry, it's early on Monday.
Yeah, I know. No, they're not estranged. They're together. They are. They're on the same side. Okay. So Z. This is a Z. I hope he wants this to.
You should tell him it's in the office so that he will look smart.
No. I'd be like telling a young, like, German Shepherd puppy to, like, just have at it. Yes, son, I have the phone here. Put on your mask and come get it, okay?
No shoes?
Yeah. Make sure your shoes are on. Son, I am teaching right now. Okay? I'm going to stop talking to you. You can come get the phone.
Does he get like breaks?
Bye-bye. Yes, that's what this is. This is a break. This is independent work time, where he's supposed to work by himself. Like he's 8. Okay? What 8-year-old goes, oh, I better get on that independent work time.
We're college students and we still don't figure it out.
We're sort of maybe getting there.
What independent work time means when I'm not in here with you lovely people is it means, oh, let me stop my job and become a second grade teacher. Okay, enough. This is not their problem. Anywho,
It's entertaining though.
we got to do another E2 elimination so we can get to our final product here. Actually, I should have given you the whole. So potassium OH, tri They are the proton and this leaving group. They're in the same plane. Okay, so they are periplanar, but now they are syn. They are not anti. And in reality, the second step is why you are cooking this up. What is it, 130?
130
Or
or
even
40.
higher?
Thought it was 130
No, it might be 160. Anyway, that's why this second elimination reaction, that first one would probably go at room temperature. Okay.
It's 190 though.
190 or 195.
Oh, okay. Yeah. You have a great deal of conjugation here, right? You have a benzene ring there, you have a benzene ring there, they're connected by this double bond, so you can do resonance, all day long with this intermediate. What that means is, in all likelihood, because of that conjugation, the energy of activation to do this first step and create all that conjugation is very low. Okay. But here we have a syn arrangement, so it takes the 190. There it is. All right. And all right. Okay, so yeah, that's how the reaction works. The setup for the reaction is just like lots that you have done now. Okay? You're just using the air condenser.
Because that's what I
There is something where it asks you to adjust, and I changed the wording on the new one that I'm going to give you in a minute. But it asks you to adjust the amount of reagents. Really all that means is the second step tells you how much hydroxide to use, assuming you have 400 milligrams of dibromide. Well, we don't know how much dibromide you have. That's the first thing you're going to do today is weigh your product from last week. So if you end up and you find out, oh, I only have 330 milligrams of dibromide, oh, calculate what percent of 400 that is. Maybe that's 80%, okay? And then use 80% as much as hydroxide. That's all there is to it, okay? All right. Okay. Oh yeah, there it is.
pretty sure.
Okay, so air condenser. Blue nut goes over it first, then the O-ring. Okay. And those guys screw together. And now I can suspend from this guy. As always, make up your apparatus dry, and then go get your chemicals once you have them. Okay. Make sure you got gloves on today. Hydroxide is very corrosive. It's worse than strong base is worse than strong acid. Okay. Yeah, I mean the reaction's pretty straightforward. Okay. You cook it for the 20 minutes. Let it cool, okay? You add water, give it a crash out. You're then going to, hang on just a second guys, hang on before you set up, please. You're going to collect your stuff, get a first funnel again, okay? And as always, use your trap and stuff. So you get your crude product into your Hirschfeld, okay? If you leave it here and it's drying, the vacuum's pulling air through it and stuff, it is drying. Leave it on there. I can't remember if the directions say it or not, but leave it on there to dry for like maybe 5 minutes, okay? The reason being is that this is going to be your crude diphenylacetylene, all right? And we're going to take a melting point of that. It's going to be a little bit accurate if it's wet, okay? So the drier we get it, the better, all right? We are then going to recrystallize it, okay? And show you how we do that. That's the thing I made a nice picture of. The way we do, the way I explain recrystallization, when we first did this reaction to make diphenylacetylene, we just jam in, I think, 5 mils or whatever it says of water into there, okay? And instantaneously, like organic molecule, that's not going to be soluble in water, okay? So it does what we call crashes out of solution. That's a fast precipitation. Basically, this is all, I don't want to be in this solvent. Bam, really fast. Crystallization, I always give the analogy of you're at some school or church function and you're stacking chairs, all right? If you tell a bunch of 6th graders, stack the chairs and there's ice cream outside in 5 minutes, what's it going to look like? It's going to look like hell, right? They're going to be upside down, they're going to be thrown, they're going to be crazy. That's what it is when you throw in the water. Bam! Mother Nature just stacks everything. Impurities get stacked in there. It's not stacked very evenly. The way to get nice, pure, high purity crystals is if Mother Nature can stack the molecules, taking her own sweet time, really careful, okay? So what you want to do is you want to find a solvent system. The way that you can make it possible for Mother Nature to stack the molecules at a slow rate is find a solvent where it's not soluble at room temperature, okay? It doesn't dissolve at room temperature, but it will dissolve if you heat it up. Heating increases solubility almost universally. All right, so you want a solvent system, and in this case, it's 95% ethanol. Okay? Oh, son of a nutcracker! That's plugged in. Yeah. Okay. Anywho, sorry.
You said this laugh, I was like, little feral.
Glad I said nutcracker. Anywho, so for diphenylacetylene, it's 95% ethanol. So what we're going to do is we're going to put it in here, okay? And then you put your stuff in there, and then you put the 95% ethanol about 1 centimeter above wherever your crystals stop, okay? No more, because you can always add, it's difficult to get it out of there, but you can always add more, no problem, okay? Then you're going to put your spatula, and I don't think I have one. You put your spatula down in here, and this is the fancy picture I drew for you, which I will show you in a minute. Your spatula goes down in there, and then this dude can just sit right in that one. Okay. Oh no, that one. All right. Spatula's in there, and then you turn this up to like a 3, and you just start twirling the spatula, trying to get it to dissolve. Okay. You know, if it doesn't dissolve, you add a little bit more 95% ethanol. Okay. Once you can get it dissolved, and every once in a while you'll see the, you know, there's a lot of lint in the world and in this room. So if you see this tiny little hair, don't break your back trying to get it to dissolve and stuff. You want the crystals dissolved. All right, once it gets dissolved, then we're just going to raise it up here, okay? And we're just going to let it cool at its own pace, all right? It is soluble hot, it ain't soluble cold, so that's our way of slowly creating an environment that Mother Nature wants to stack those molecules. Okay? Does that make sense? Occasionally it doesn't happen. You know, they're willing to stay in solution, okay? And then you'll add a drop of water or so. Okay, room temperature water, 1 drop, as little water as you can. The slower the crystallization, the more pure the stuff is, all right? Once you've sort of started the crystallization, before you try to isolate your stuff, go ahead and put it in ice water, as the instructions imply, and to make sure that you get every little nugget out. Okay? All right. Now, so in the end, you'll have room temperature, or cold now, cold, 95% ethanol, and you'll have your recrystallized, beautiful, pure stuff down in here. It's really too small at this point to pour through the Birch foam. Okay? So isolating it becomes an issue. It may just go all the way through, et cetera, et cetera. And that problem is exactly why you're using this fancy Craig tube, because this fancy tube helps you isolate small quantities of precipitate. Okay? All right, so this is how you do it. You take the piston part, and it goes like that. Okay? You then do not use glass centrifuge tubes that are in here. Use the plastic centrifuges over there. Okay? First, you tie a string on here that's, I don't know, maybe 10 inches. Okay? You tie a string around the piston. Okay? We've got thread over there with which to do that. Okay? So string around the piston. All right? Now, that's a ground glass joint, and that's ground there too. So they fit together pretty well. Okay. They fit together so well. Okay, I put the centrifuge tube. I put them in my hands like this, and I go whoosh. Okay. They fit together so well, actually, that the liquid, the solution with the precipitate and the ethanol and everything will probably stay up top. Okay. Your string is out here. All right. But when I put it in a centrifuge for 60 seconds, all the liquid will find its way through the ground glass joint. Okay? But that piston that's now sticking up will stop the crystals. So the liquid will be down here, the 95% ethanol will be down here, and the crystals, now without the centrifuge tube, the crystals will be stuck right there. And you can pull this guy apart and then put it on your watch glass. You're going to put it on another watch glass that you pre-weighed and let it dry till next week. Does that make sense? I did that fast because I got a beautiful picture for you. It was up until midnight making. Okay, one last question. What's the string for? String for? Why did I put a string around the piston?
So you can take it out?
Yeah, so I can get that guy out. Otherwise, I would have to do this, and then all my powder, all my crystals just fall around the piston and fall back down into the solution where we need to work. So I need a way to be able to pull that bottom piece out that I can't reach with my fingers, so I use the string. Well, all right. We're going to try to get the melting point of the crude. Remember, or maybe I didn't even say that. Shit. I mean, I did say make a melting point sample. I did. Okay. Yeah, make a melting point sample, just enough to get it into the melting point tube. Yeah, and then set it aside. At the end, once you've put your recrystallized stuff on its watch glass that's pre-weighed, waiting for next week and stuff, tape, then you're going to take the melting point of your crude material, your unrecrystallized stuff. Okay? And then next week, we'll take a melting point of your recrystallized stuff. And we'll compare and see if you improve the purity. Questions?
Are you doing the IR?
No, not doing the IR today. If we do the IR today, you're going to get a big hump around around 3,000. And it won't, there's no alcohol or OH, it's water. It's the water that's been exposed to it. So we'll wait till next week. We should have plenty of time, especially with only 8 people. Okay, any other questions? All right, let's do it to it.
Oh, did you have another one of these that had like a change in it?
Yeah,
Okay.
yeah, that's what I printed out.